My name is Bryn and I'm an MVP based out of Christchurch, New Zealand. The executive summary of all this is I wanted to be an electronics engineer, but I partied really hard in my first year of university, so fell into computer science totally by accident. In the mid-90s, I was working on SCADA and mobile radio solutions, which got me interested in the sort of technologies which would be useful for the brave new world of the Internet of Things. These days, I work mainly for a fintech company building software for managing large portfolios of financial instruments. We refer to the product as boring maths for accountants or maths for boring accountants. Either way works. The fintech pays the bills, but my IoT projects are way more interesting. My partner is a digital technology teacher and an MIE, a Microsoft Innovative Educator expert. So my stretch goal is to be a kept man. The main problem is that teachers don't get paid that well, and I have expensive tastes. I also run a maker club at a local girls' school and work with a couple of year 13 scholarship students most years. On the left is a pulse rate monitor, accelerometer, and GPS. And yes, that is a Systema box for tracking the performance of a horse. I was amazed that a pulse rate monitor, which is designed to clip onto a human ear, worked quite well on a horse. We actually had to shave about a 50-cent piece size bit of the horse's ear. It was a very patient horse. On the right-hand side is one of my students testing a sensor for monitoring the water quality in the lake next to a family farm. It uses the ultrasonic ranger from a car bumper to measure the depth of the water. You can see the tube is about 2 meters long. I wrote down 20 centimeters. 20.0 centimeters on a piece of paper, and then she went to the plumbing supplies place and by accident missed the dot. She said it got some real odd looks on the bus to school in the morning with a pink backpack carrying a 2 meter long tube over her shoulder. Floating in the water is a turbidity sensor from a Westinghouse industrial dishwasher. They recycle the water over and over, and then when it gets too grungy, they get a new load. The measurements were then sent over a LoRa radio link back to the farmhouse and then onto Adafruit.io for graphing and alerting and stuff. It's the middle of winter, so the pool water is a bit green. My specialist area is weird. Pretty much every job except for the finance company is a bit weird. People call me with odd problems they want to solve. Last week, a local ag company gave me a call about a computer vision project they were working on. So I went on a class trip to Lincoln University, where there's a research dairy farm, and spent some time in a milking shed. I then spent Thursday afternoon drawing minimum bounding rectangles around cows' butts to test the model. So here we go into the meat of the presentation. Out beyond the edge, the devices are really small. Often they're powered by batteries or solar. I've selected these 4 devices because they all come from the same vendor and you should be able to get a feel for the cost of the bits. On the top left is a Arduino LoRa module. With a small solar panel and a LiPo, it could run forever. They cost about $20 US. On the top right is a Arduino Bluetooth. With a larger solar panel and a larger LiPo, it would run forever as well. It costs about $20 as well. Halfway down on the right is a Arduino ESP8266. With an even larger solar panel and battery, it would also run forever. It's a bit cheaper. They're about $14. The ESP8266 chips are pretty well priced. On the bottom right is a SparkFun ESP32 single channel LoRa gateway. It runs at 240 megahertz. It's $35 US, but with all that power, you're most probably going to need a wall wart to power the thing, or a plug pack. For reference purposes, my first work computer was a 10 megahertz 286 PC clone running MS-DOS. Power consumption is critical for LoRa modules and LoRa applications. The Arduino has 2 LEDs on it. One is on all of the time, and the other is on when the battery is charging. The LED consumes roughly 15 milliamps. The LoRa module, when it's in receive mode, consumes roughly 30 and about 100 milliamps when it's transmitting. So if you took a pair of wire cutters to the permanently on LED, you'd save roughly half your power consumption. Or if you were running the custom version with a security module and a crypto store and a unique ID that I designed, you could just remove a jumper. Microsoft talks a lot about Azure IoT edge devices. In my world, they're an awfully big hammer. It's mainly about power consumption. An RPi 4 uses sort of 5 watts. A Tinkerboard, sort of 10-ish. A Jetson starts at about 15, but if you start doing heavy graphics work, it can be more. And the Asus industrial box on the right has a 65-watt power adapter. That's to cope with the power consumption of the CPU and any peripherals that you attach to. In this case, it's got sockets for cameras and Wi-Fi and so forth. For comparison, the Arduino device that I was talking about on the previous page uses about 1/10 of a watt, and even less with wake on, interrupt, and deep sleep when idle is enabled. So the power consumption differences are significant. Beyond the edge, where I usually hang out, there's no operating system, definitely no containers. Though, with some recent work by Edge Impulse, you may be able to get ML. I'm working on a project on the side at my son's school, counting people going down the bus lane. They want to be able to differentiate between road bikes, mountain bikes, cargo bikes, and mammals on racing bikes. So, the magic glue in Azure land. For Azure, for larger deployments, there can be an awful lot of devices. For example, if the Christchurch City Council wanted to monitor all the water meters in town, they would need about 130,000 water meters. The cheapest useful Azure IoT Hub SKU is US $25 a month. And the largest, which is an S3, which maxes out at 1 million devices and 300 million messages a day, is about $205. They're very focused on security. Data is secured, access is secured with SAS keys or X509 certificates, and some devices have even got trusted platform modules. There's IP whitelisting and VNets, basically the works to keep everything secure. Device communications is always secured by TLS. You can't connect without it. A long time ago, AMQP came from the finance world. It's great. It's being used for high-speed trading and things like that. It's great because you can pull connections across a single socket. MQTT came from the manufacturing industries, originally by IBM. It was an extension on the MQ series messaging protocol. And of course, HTTP came from the Wild Wild Web. In addition, Azure IoT hubs have the concept of device twins. A device twin is a GOB JSON, which, if you do it right, can be automatically synchronized between the two devices. I tend to use the Azure Device Provisioning Service, which is a global service. It supports the management of identity from when the device is manufactured in a factory all the way to through when it's deployed. And it means you can do largely a hands-off deployment. Both Azure IoT hubs and the device provisioning service have APIs that you can call from your applications. There are Azure IoT Hub Gateways. I have built a few of these. There are 3 types. There's a transparent gateway, a protocol gateway, and an identity gateway. It's all about identity with Azure IoT hubs. With a transparent gateway, the leaf nodes are Azure IoT Hub, have Azure IoT Hub identities. It might be a series of Percept boxes out in the factory or some Azure IoT Edge devices running some variety of Linux. It converts, it's basically store and forward, and it can manage updates and things like that. A protocol gateway converts one protocol to another, and all the leaf nodes usually have the same Azure IoT Hub identity. This could be used, and I've done it, and I'm not proud of it, for supporting HTTP with no TLS. We had a cellular modem which couldn't do TLS. It can also, I've used it for connecting devices which support CoAP. CoAP is a lightweight industry protocol. It's sort of like HTTP over UDP. Another sort of application for this is sometimes cellular modems, the headers, I can't make the headers big enough to fit SAS key through in the authorization header. So you have to do some magic smearing the SAS key across 2 headers. It's pretty fugly. Identity gateways. Basically, the leaf nodes are mapped into unique Azure IoT Hub identities. My Lorawan, the Things Network Lorawan Gateway does this, so we'll talk a bit about it later. If you're connecting to Azure Iot Central, the type of gateway used is important. With a protocol translation gateway, adding and removing sensor nodes requires template change, which is a real pain in the ass. What you really want is an identity translation gateway, but they require a lot of work. They're not great to write, and the scope for disaster is high. On the right is a dual band 433 megahertz and 915 megahertz LoRa gateway that I use against Azure IoT hubs. It's designed for educational applications, has a really numpty ASCII-only protocol. It's really easy for students to interface with. LoRa is not LoRaWAN. The terms are used interchangeably, and it's really confusing for people who've done a lot of it, let alone for newbies. LoRa is the physical layer. It basically gets buffers of bytes from one place to another with an optional CRC. This is a really gross oversimplification. Think about it like a CB radio. You press the button, you transmit, and lots of other people can hear you. It's used sub-gigahertz frequency bands, which are really good for in-building penetration. They'll reach tens of meters into a building and even into a basement, which is great for power meters and water meters. There are other wide area networks which use LoRa that aren't LoRaWAN, and these are starting to get a bit of traction. The LoRaWAN specification is managed by the LoRa Alliance. You'll see on the right, there's a chip. Semtech build these chips, but they also let you can also buy the design and include it onto your silicon. People then take those chips and mount them on modules, which is the top right, which gives you LoRa, and it takes care of all of the RF magic. And then the bottom two modules are LoRaWAN. Inside those tin cases is a microcontroller, which does all of the high-speed timing and so forth, which then usually interoperates with your code via Haze AT commands or SPI or I2C bus. There are lots of vendors for the hardware, but you've got global compliance issues. There are different frequency bands around the world. There are different rules about duty cycles and power levels. The effective transmission range is somewhere between 5 and 15 Ks, but your mileage may vary depending on whether you're in a town or in the country. Class A devices send an uplink message, wait for a wee bit, and then go back to sleep. Class B devices send a message, wait for a wee bit, go to sleep. They basically extend the Class A device, and then every so often on a synchronized time, they wake up and listen for a new message. For fans of the Arduino, have a look at the LMIC code, which was originally developed by IBM, and get the MCCI Katina one, which has been kept reasonably up to date. I was going to give it a go, but I'm not certain about whether it supports a band channel called AS923, which is used in New Zealand. Some of the newer LoRaWAN devices have even got a hardware security module, like the ones you normally see in a 19-inch rack mount cabinet storing credit card encryption keys and stuff on board, and they're tamper resistant. If you try and leave the lid off, they destroy themselves and stuff. LoRaWAN is not designed for low latency streaming video. It's for applications that send tens of bytes every hour or a couple of times a day. For most LoRa applications, power consumption is the key. I sit down, some of the vendors even provide spreadsheets so you can work out how long the batteries will last. On the top left is a door sensor. So from my hand, you can see how big they are. It costs $17 US. You get a message every time the door is open and closed, and then one message every day just to check that it's alive. They quote the lifetime of the battery and the number of messages sent. So it's good for about 2,000 packets in a good coverage area, and about 300 packets in a bad coverage area, because it has to transmit harder and transmit longer. The rack whiz node, the black one on the right, you can see roughly how big it is. It comes with a belt clip and it's a GPS tracker. It's got a accelerometer, a magnetometer, a GPS, and a Lorawan module, and you can use the magnetometer and the accelerometer for working out whether someone's taken a tumble. The temperature and humidity sensor on the top right, you configure it with Haze AT commands. You can plug in an external sensor with a lead and monitor other things like counting pulses out of a water meter and things like that. But it's so focused on power. With a Haze AT command, you can say, hey, turn the sensor on, wait for a bit for the readings to stabilize, and then take a reading. It has a built-in 2400 milliamp hour battery. You can configure the update rate via the Haze AT commands. It stores 3200 readings on board, and the battery can last for 10 years if you have a slow enough update rate, but I usually plan for somewhere between 2 and 5 years. We've got weather stations, we've got single phase power consumption. That one is a CO2 level. You can get ones like that, which are indoor temperature and humidity, or devices like this, which is a GPS and lone worker tracking pendant. With such limited power and small bandwidth, you've really got to reduce the size of the messages. You don't want to keep the transmitter on for any longer than necessary. The less time the transmitter is on, the shorter and the smaller the packets, the longer the batteries will last. The Cayenne LPP format was originally created by the MathCAD people, my devices. And it's the most common way of munging together a series of values into the smallest possible size of bytes. The latitude and longitude are stored in 3 bytes to save space, which leads to some interesting quantization issues. You can see the positions around my house are roughly 10 meters apart as the GPS wanders. The Things network supports custom payload encoders and decoders, but these are written in JavaScript. You can use specialized ones for where you need more accurate position reporting and things like that, or you've got data which isn't supported by the Cayenne LPP. These are all Arduino MKR devices, and I've just used those so we can compare the cost of the modules. Wi-Fi uses too much power, so that's gone. The narrowband IoT modules are too expensive, and the support for them globally, some of the more advanced features, is patchy. So the main 2 competitors are the Lorawan module, which is on the top right, and the Sigfox module. One of the main problems with Sigfox is uplink messages are 12 bytes, so you can just get a GPS position. Downlink messages are 8 byte, and you can send a maximum of 140 a day. Lorawan networks usually have some sort of fair use policy. So the Things network forum suggests 30 seconds of uplink a day, so that takes into account whether you're in a good or a bad coverage area. 10 downlink messages a day, so you can use those for instructions to the device to reboot or change its update frequency or confirm a message. And then your payloads are usually up to 51 bytes, but you can go a bit larger, but that negatively impacts on your battery life. There are in Australia and New Zealand 4 commercial offerings. The prices are usually a bit less than cellular because the networks are cheaper to deploy and to operate. You don't have to buy Spectrum because they work in the ISM, the Industrial, Scientific and Medical band, so you don't have to have an expensive auction. They've usually got APIs for mass provisioning and management of devices, and they focus on a low-touch operation because to make a profit, they can't have a huge help desk. If there's no coverage at your place, they can often put in a site to increase the overall coverage, or sometimes they'll give you a base station if you're out in the middle of nowhere. Under the covers, I think the Australian mesh network might use the Things industry stack. Microsoft have done an Azure based LoRaWAN networking implementation. It's a really interesting project. Laurent E and the other contributors have done an amazing job, but it runs on Azure Iot Central, so move on, nothing to see here. The Thing Stack is an open source product developed out of Amsterdam. When I first looked at it, there wasn't a lot of love for Azure. There are several parts to the Thing Stack. There's the code base. Then the Things Network is a global community of people interested in LoRaWAN who make their infrastructure available to others. If I put up a base station, that's one over my shoulder there, and they share it out. There are demo integrations with AWS, All Things Talks, Ubidots, Adafruit, and a few others. But the sample integration with Microsoft Azure was pretty lame. It was a couple of Azure functions and it didn't really work that well. There's a sample Microsoft integration based on the Azure Iot Central device bridge, but that rapidly got out of hand and my poor little brain couldn't cope with it. There's also some Benjamin C in Europe has done a project how to deploy a Things Network implementation onto Azure, and that's quite interesting. If you've got you can start small. You can work on the free tier, or the community tier, or you can start on the free tier. It basically comes down to whether the deployment is running in your cloud, their cloud, or you can even do it on-prem. It starts around $200 to $600 a month for support, and then there is an additional cost per every 1,000 devices. I found that their help is pretty responsive considering I've got a free trial account. They answer my questions pretty well. The Lorawan network is, the Things Network is a community network. You can see there's an awful lot of base stations. Earlier this year, there were 170,000 base stations in 151 countries around the world. In New Zealand, there are roughly 120 gateways doing AS923, which is the regional standard for New Zealand and through Asia. And in Australia, there are roughly 920 gateways running a combination of AU915 and AS923. I have a couple of gateways around home, and then I'm looking at deploying half a dozen gateways in local schools for the kids to do projects with. Think of it as a cellular network for devices, and with some of the top-end configurations, you can even globally roam, so you could use it on ships or yachts or things like that. There's actually a crowd here in New Zealand who are using it for yacht tracking. So if your yacht gets stolen, you know about it. The rack, that device over there, is designed for indoor usage. It's great for smart building applications or getting a new system up and running. The other devices on the right are weatherproof. The varying number of antennas is based on whether they've got an LTE modem or multiple frequency support and things like that. You might get 10 to 15 Ks in the country, which is great for smart ag applications, and 3 to 5 Ks in urban areas. If you get your antenna higher and structures that you're trying to reach into don't have too much steel, it can be pretty good. They have GPS modules for synchronization to get really accurate time at each device. If your device can be seen from more than one field gateway, they can do a rough sort of triangulation and give it an approximate location of the device. Of course, the more field gateways or the more base stations, the more accurate the location. It's one of the other things that the Things Network and LoRaWAN have. All of the base stations are listening all of the time. So if your device can be heard by multiple base stations, there's some deduplication magic in the background, which if you send a message in and it's received by 2 or 3 base stations, it works it out and only sends your client one. Base stations often have a 4G option to provide backhaul if the main form of connection goes down. Getting a network connection in a school or something like that is really painful. Some of these gateways have a built-in LoRaWAN server, which is based on the chip stack code. You need to keep this running in all weathers. You can bung on a solar panel and a battery pack. It'll last for 3 days with no sunshine. Another important thing is, because these are mounted high, you really want a lightning arrestor. These are $32 a pop, and they will stop a lot of tears when, in the unlikely event, a bolt of lightning happens to hit your base station or nearby to your base station. So this is the architecture diagram of the gateway. Originally, I had a look at the Azure Iot Central bridge, but it wasn't what I wanted. I had to go out building a TTN version 2 gateway. Problem was the Things Network version 2 was soon deprecated. And I used an HTTP integration, and it was just a disaster. It had lots of tech. It had Azure Key Vault, HTTP storage queues, HTTP triggered functions, storage queues, storage queue triggered functions, lots of magic, device provisioning service integration. Basically a buzzword compliant project, which was, in the words of management, negatively impacted by some suboptimal design decisions. I also had a few snags with it being too complex to debug, operate, and deploy. I started again, and this is the solution I ended up with. Got to do some background about messages. LoRaWAN has the concept of a port. Think it's TCP/IP ports. It's for the routing of messages. You can control where a message is inserted into the queue. You can control the priority of a message before it's sent. You can choose whether your message to the device is confirmed. This can consume your limited number of downlink messages. Also use with care, as it can badly interact with the Azure device client baked in retries, especially if it's a Class A device, which only connects every hour or two, or maybe only once or twice a day. Binary payloads are base 64 encoded, and JSON payloads are encoded and decoded by the Things Network. Custom correlation IDs can be used to keep track of message delivery in your application. It's got a registry of devices. You can call it with gRPC or a RESTful API, which has an open API spec. I used the Swagger and NSWAG to generate my clients. It gives you CRUD for applications, CRUD for end devices, CRUD for support for custom attributes. I decorate some of the application and device objects with attributes for whether they're partaking with Azure and other stuff. One thing that caught me out was that I used camel cases for the devices that I'd manually configured in Azure Iot Hub, but the Things Network forces you to use lowercase. It really caused me a lot of pain. The other thing I found was that the Things Network assumes that you've base 64 encoded, Swagger assumes it's base 64 encoded, but the Things Network was actually BCD encoding stuff. When you get to integrate, you get messages sent to you and send messages via. I use JSON to C# to generate my DTOs from the sample messages, some of which were actually broken. You've got to be careful if you use an HTTP integration, because the API keys can be embedded in the sample callback URL inside the uplink payload. You've got to be careful with MQTT, with case-sensitive topic names, and you need to pay attention to quality of service, because sometimes the Things Network will spit at your choice of quality of service. I use the MQTT managed client because it automatically does retries, in the way that it did callbacks was a lot easier. To connect to the Azure, I use Azure Iot Hub connection strings, the ones where you just shove in a device ID, or I use the device provisioning service. For larger deployments, the device provisioning service is the way to go. And the little devices like this one have a QR code on the front, so they can be automatically provisioned in the Things Network. I've also got basic DTDL, device to indefinite language support, and you can get the ID from either your Azure Iot Central, a vendor, or if you're feeling brave, you can handcraft your own, and there's some support for that in Visual Studio Code. Sending a message from a custom application talking to an Azure Iot Hub, you've got to provide a port. That's the only mandatory thing, and I will default the priority queues and then the payloads. It assumes that if the payload is valid JSON, it's going to graft it into the formatted payload bit. And if it's not valid JSON, it will assume that it's a MIME encoded string and put it into the raw payload. True, TRUE with a small t, is valid, a valid piece of JSON. And this caused me some pain, because the first time I used a Boolean sensor pop, everything went wrong, because the it was valid JSON, but when I grafted it into the other JSON, it just broke everything, so it required some magic. The port numbers are used for routing, so you might have GPS positions coming in on port 5 and routed to a GIS app. The cargo temperature and humidity of your truck might come in on port 10 and be routed to a delivery tracking application. You can see in the screen grab, the payload raw is the MIME encoded message, and then it's been unpacked to barometric pressure and temperature. The huge number of decimal places is a pain, but they are not actually true. It's basically up to 1 decimal place is valid. I don't know why it puts in all of the other ones. Azure Iot Central is great if you just want to do some graphs and send some emails when stuff goes out of bounds. It has some limitations, and I'll talk about those. It's basically no code. You create templates for devices, so it's really designed for systems where there are lots of devices which use the same. There's some specialness the way commands are sent to devices. The formatting of the payloads is surprisingly complex and prescriptive, which makes it awkward to talk to devices. There are 3 pricing tiers: 8 cents a device, 400 messages a day; 40 cents a device, 5K messages a month; 70 cents a device, 30K messages a month. And there's a free version which works for a week. You don't have a lot of control over the message properties for LoRaWAN devices, so these are configured on a application by application means inside the app.settings file. With Azure Iot Central, it's got telemetry, it's got commands. I had problems with a weather station which returned hectopascals, and that wasn't supported. If you have to transform some data, you have to send it out and then bring it back in. With the commands, you have to use an offline command. Online ones aren't supported, and you can have request payloads. Response payloads are not supported by my integration, as commands can take minutes or even hours to deliver. If you send a command with no parameters, the command string is just an @ sign, and I have absolutely no idea why. I also do some tweaking of the telemetry payloads. Azure Iot Central expects lat, long, and alt. The JSON payload decoder returns latitude, longitude, and alt. So I do some magic mapping to sort it all out. Once you've got it into an Azure Iot Hub, you can shift it out to other things. Most Azure resources have got baked-in support for publishing and subscribing to events. I use Azure storage queues quite often as a simple way of getting messages into a bucket where I can look at them. The message format is quite complex, but there are libraries to support it. I really want to try hitching SignalR up so I can update one of the maps on my tracking app. I can then feed stuff into logic apps. At the FinTech, we use Twilio for 2-factor authentication. I figured I'd send myself text messages when sensors failed or readings got out of range. Setting up Twilio was pretty easy after I'd figured out how the content type of the dynamic content was set. It worked second time. I hadn't started the logic app. Problem was I'd backed up a whole bunch of messages and I rapidly burnt through all of my credit. On the right is my Nokia 7 phone, and on the left is the debugging output from my first Arduino. And we're going to talk a bit more about that later. I don't know what it is about Stream Analytics, but every time I run it, I burn through all of my credit. I always get an email saying, do you want to remove your spending limit? And that worries me. I get like $250 a month. Most people have a love-hate relationship with Power BI. It's one of my core incompetencies. In my gigs, I usually get the telemetry data and configuration information to a data store. Then I knock up yet another hideous dashboard to show the telemetry working. Then a highly trained Power BI professional configures visually appealing, because I'm slightly colorblind, dashboards and reports for end users. So people thought that there was no .NET right out at the very far end. How many of you remember the Fairs Spider? It was originally a project developed by Microsoft Research in the UK, and it was to let them explore small devices, and it actually runs a cutback version of .NET. I can build and debug programs on an embedded device. That's one there, which has got Wi-Fi, a 200 megahertz processor. There is secure deployment, secure update. They've even got a FezBit, which is a more powerful version of the microbit used for teaching. They're really designed for commercial products, you know, POS systems and petrol pumps and things like that. They've got all of the security stuff baked in, and you can buy modules like the one on the right or SOMs on the left, which are great for integrating into your own product. I've built some libraries for that. On the right is this one here. It does LoRaWAN. Well, it will in the next couple of days. It's just started to get working. On the bottom left is a Fezduino talking LoRa. In the middle is a Fez portal, which on the back there's an LCD talking LoRa, and on the bottom right is a Fezduino talking LoRaWAN with a rack 811 Fezduino module. That'd work in Oz, but it won't work in New Zealand because they haven't got the AS923 channel set properly. In New Zealand, you can only join the network on the first 2 channels, whereas that one tries to join on any of the 8 channels. And then if it doesn't randomly select one of the first 2 channels, you just have to keep on pressing reset until it does. Another option for .NET on devices, out of the wreckage of the micro framework came the nano framework. It's amazing that I can deploy and then debug an application running on a device from Visual Studio. It's not quite as smooth a process as with the tiny CLR. Jose, Adrian, Robin, and Peter, the core developers on it, are really nice. There's an active Discord community, and they provide reference platforms and sample apps, and I'm even a contributor. The build process, you can actually take the source in C++, build it, deploy it to your device, and run it. The build process is non-trivial, but after you've got it going, it works pretty well. And the bonus is, I guess I'm about to get censored, there aren't any arseholes on the forums, which is good for newbies. If any of you have been to the Arduino forums, there are some people with a very limited amount of patience, which pisses me off greatly. These are the devices I've been working on. On the left is a Netduino running a LoRa system. The Netduino was created by Secret Labs. It went pop, it then became Wilderness Labs. And I've got 40 of these lying around because I used to teach them kids how to code. In the middle is a SparkFun single channel ESP32 gateway running the .NET Nano framework, but I'm actually running backwards, so it's a client, not a gateway. The Nano framework works across lots of STM32 boards, ESP32s, and they're always increasing the board supported. On the right is a STM 791, which does LoRaWAN, but on the back is a LCD screen displaying the messages from my device.